Welcome. The title of today's lesson is Operations with Complex Numbers in Polar Form. And this lesson actually represents the day 1 part to this, as you'll see the day 2 on the next notes worksheet. So we're going to do 4 operations with complex numbers over the next couple days. Today we're going to set up multiplying complex numbers in polar form. We're going to set up dividing complex numbers in polar form. And then we'll at least set the foundation for doing raising a complex number to a particular power. And then on tomorrow's notes worksheet, we'll continue with powers, and then we're going to do roots. Some pretty heavy, difficult math in that second notes worksheet, but obviously we'll walk through it step by step. Okay, so let's start it out here. It says let Z1, so one complex number, here's your R cosine theta plus I sine theta, so one complex number in polar form. And then here we go, everyone, a second complex number in polar form, hoping everyone sees that, R cosine theta plus I sine theta. So 2 complex numbers. If we multiply those together, actually some good things happen. So let's see. We're going to do a Z1 times Z2. So I'm going to basically take those 2 complex numbers and I am going to multiply them. The way it works out, everybody, is that you multiply the R's together. So R1 times R2. So the moduli, so to speak. So we're going to multiply R1 and R2. And the way it works out with the thetas, it's kind of interesting here, you add the thetas. So there's cosine of the sum of the thetas, and then everybody combine the thetas together via addition, and same thing there, I sine of theta 1 plus theta 2. And so that's what it's going to look like. You have a second blank right here. I guess here's the way I would say it, is you multiply the R's. So I'm going to write it like this, be nice and formal with it, and then so just put R next to it. So multiply the moduli together, the plural of modulus, and add the arguments together. The arguments would be your theta. So multiply R and add theta. And that's how we get our new complex number in polar form. Now, what we're going to do is just take a very quick peek at and prove this. So it's one thing for me to kind of give it to you there, and that's exactly what we're going to use. But I think it does benefit us to actually sort of see why this does play out. So it says, example 1, prove that this is the formula for the product of 2 complex numbers. And here's what I'm going to ask you to do, everybody. Give me a Z1 times Z2 right here. And so this would be the first complex number. So I'm going to do cosine theta 1 and I sine theta 1. So there we go. So I'm going to do that times, and then R2. So that second R times cosine theta and I sine theta. All right, so we're going to do this times this. Now, here is the thing. One part of this is as easy as it gets. The other part creates something that we haven't seen in some time, but I will say we have seen before. So let's see if we can identify that piece as we go through. Now, I hope everybody would be in agreement that this is all multiplication, right? This times this times this times this. And we all know multiplication is what is called commutative, meaning the order doesn't matter. So what I'm going to do here, everybody, is take those 2 R's, and I am going to multiply them together. In fact, just like it says above, I'm supposed to multiply the R's together. Now, everybody, I'm going to put these 2 things, and I'm going to multiply them together. So I guess I'm going to do it this way. Cosine theta 1, I sine theta 1, and then cosine theta 2, and I sine theta 2. All right, I hope everyone's with me right there. Just very simply, order doesn't matter. So I'm going to multiply those and then multiply these. These 2, exactly what the formula says. Now, where the heck did this come from? Let's find out. Now, does everyone see that in essence here, I have these as really 2 binomials that I would multiply together? And the way I'm going to multiply them together, everybody, is through foiling. So I'm going to do first, outside, inside, and then last. Now, here's the thing. To really see this in action, I'm going to do exactly that. I'm going to FOIL, but I'm going to do it in a slightly different order. So here's how it plays out. And I would be curious if you see something worthy here. So everyone, huge parentheses as we go through this. And here's the premise. Firsts, everybody. This times this. So that's cosine, cosine. Okay, everyone all right with that? So first, this times this. Now, as a matter of fact, instead of doing FOIL in that order, I'm going to do the L next. So what I'm going to do, guys, is multiply the I sine theta 1 and I sine theta 2. Now, everybody, here's what I would ask you. Do you all remember what I times I actually is? I times I, of course, is I squared. And I squared, everybody, is -1. So what that's going to do is change this to a minus right there. So I squared -1, and then sine theta 1, sine theta 2. Okay, now stare at that for a second and think about that one. You have seen this before. Crazy as it sounds, you have. Alrighty, now the outside and the inside, not a whole lot goes on. Does everyone see? In fact, I'm going to do the inside first. Does everyone kind of see? Not much to do there. I've got an I, sine this, and sine that, and then this right here, same deal. If it's okay with you, well, actually, I'll write it all out, at least initially here. So if I do the inside first, I get I sine theta 1 cosine theta 2. And I get I cosine theta 1 sine theta 2. Okay. As I said, that is some pretty complicated mathematics right there. But it's time for us to see if we can narrow this down a little bit. So one more line, and I think we are ready. There it is. R times R. No big deal there. Now, as I was ranting on about this stuff over here, I'm wondering if you noticed this piece before. So, does it ring a bell? It's been a little while. The way I used to always say it is cosine, cosine, minus sine, sine. And as a matter of fact, that little expression right here, just this part, is what is called the sum formula for cosine. Don't know if you remember sum and difference formulas from way back when, but that is what's called the sum formula for cosine. Do you remember this piece, everyone? This isn't distribution. We would say cosine, cosine, minus sine, sine. And there it is. And let's go over here, because watch what else comes up. Now my second two, these two over here, everybody. Do you see that there happens to be an I in both of them? So I'm going to pull that out. So here's my I. I pull it out. And then take a look, guys. Sine, cosine, plus cosine, sine. And if you remember correctly, just to get this moving along at this stage, that happens to be the sum formula for sine. Remember that? Sine of the first, cosine of the second, plus cosine of the first, sine of the second. And as crazy as it sounds, that's it. So Z1 times Z2, there's your proof right there. So as I said, just as a teacher, it's important for me to just show you, first of all, what it is, but also how and why it works. And so there's some great high-level mathematics to go ahead and bring that out. Okay, well, let's go ahead and utilize it a little bit here, see what you think. So example 2, just kind of work through a couple things. Find the product of the following pairs of complex numbers. They are written in polar form, and generally speaking, it's pretty convenient. So first time around, of course, we'll write everything in place and then go from there. So Z1 times Z2. I'm going to multiply these two numbers together. I take the R's and I multiply them together. So you know 2 times 8 is going to give you 16. No big deal. It's probably the easiest part of any math we've seen in a while. Now the secondary piece is to go ahead and create a new angle for our complex number by adding these two angles together. So this is just 2 pi over 3 plus 5 pi over 6. And then I sine Same thing, 2 pi over 3 plus 5 pi over 6. Okay, looks good. So multiply the r's, add the thetas. You'll hear me say that a lot when doing this particular operation. Multiply r's, add thetas. So let's go ahead and break this on down. 2 times 8 is 16. Now, everybody, let's see if we can do fractions. All right, well, let's combine them. So I'm hoping everyone is comfortable with the aspect of adding two fractions together. We need a common denominator. I'm seeing this, everybody, in sixes. So 4 pi over 6 plus 5 pi over 6. Everyone okay with that? 4 pi over 6 and 5 pi over 6 make 9 pi over 6. Keep thinking. Good number sense here, everybody. 9 pi over 6 happens to be 3 pi over 2. I think that's your new angle. The good news is you only have to do that once, of course, because the angle is the same in both. All right. Now that actually happens to be the product right there. This times this in our new form is that right there. So let's jot that in. In polar form, this is the answer. Okay, and so we got that piece. Wonderful. Now, of course, pretty comfortable at this stage, should be able to go polar form to rectangular form or rectangular form to polar form. And so let's go ahead. Let's go ahead and convert this piece. And so know your unit circle, of course. I see this as cosine of 3 pi over 2. Knowing your unit circle, you know the cosine of 3 pi over 2 is exactly 0. And then I times sine of 3 pi over 2, everybody, is negative 1. And so as a result, this distributes in just like we did on the previous notes worksheet. 16 times 0 is 0. 16 times negative 1i. And there's your answer. Not bad. Not bad at all. Two different ways to express our answer, our product. One in polar. Okay, so let's do part B. Now that maybe we have a little rhythm with this, multiply the r's, add the thetas. I think you'll like degree mode here. So 6 times 5, cosine of 40 degrees plus 20 degrees. And then I sine, same thing, everybody. Add those two angles together. 40 degrees plus 20 degrees. And that's it. Multiply r's, add thetas. And so this one, no worries at all. 6 times 5 gives us the 30. 40 plus 20 gives us 60 degrees. And if it's in polar form, I would say operations in polar form, especially this multiplication, if they're in polar form already, yeah, it's easier than rectangular. You don't have to FOIL, you don't have to do anything like that. Multiply the r's, add the thetas. And so as a matter of fact, there is one answer. Absolutely outstanding. Now, again, always looking to go forward here, so let's go rectangular on this, get a little practice on that piece. Cosine of 60 degrees, everybody, you know, you can visualize it exactly 1/2. Sine of 60 degrees is exactly square root of 3 over 2. Stuff we've been developing now for months. And everybody draw those arrows in place if you would. The r distributes in. 30 over 2, so should give us 15 right here. 30 over 2 again, so another 15. And write this however you'd like. I like tucking the I in there, but obviously it doesn't make a difference. Okay, so one more time, product of two complex numbers in polar form. Multiply the r's and add the thetas. Okay, good. Hey, let's do the example 3. It looks like it's just a natural fit with example 2a, and then we'll move on to the division. So example 3, it says, verify your answer from example 2a using the rectangular form of each number. So I took the moment, I took a little time, guys, on your notes worksheet, and I converted that to rectangular form. That's actually this right in here. And I took this, and I converted it to rectangular form. That's this piece right here. Now, again, I'm just trying to make a connection from pre-calc 1 But basically, what if I asked you to multiply those two numbers in I root 3 in rectangular form? So that's all I'm asking, to verify our answer. So in this case, convert and then see what we get as an answer when we multiply them together. And I'm going to go ahead and just do a little FOIL here. You guys can just kind of copy it down. I know you've done this in Pre-Calc 1, and I don't want to overwhelm you with too much here. But I'm going to do a little first, outside, inside, last on this and see what we get. So if I do the first, this times this, 4 root 3. If I do the outside, looks like I get negative 4i. If I do the inside, this is interesting. I get I times negative 4 times the square root of 9, which is 3. So 4 times 3. I'm getting a minus 12i there. Check that out if you get an opportunity. And in the back end, let's just make sure here, I get I times root 3 times 4 times I. 4 times root 3 is good. I times I, everybody, is I squared, which is negative 1. So this changes it, I believe, to minus 4 root 3. Hey, everyone, combine like terms at this stage. First, outside, inside, last. Look at the first and last. There they go. They're the same. And do you see what you end up getting? Again, it was nothing more than confirmation on this piece. We had it in polar form. We did that little rule from above and got our answer converted. Beautiful. If we just so happen to have converted and did the operation, of course we end up with the same result. Not a big deal. As I said, this is what you're going to be doing. More example 2. 3 was, as I said, just to confirm. Okay, everyone, let's go ahead and do quotient. And the good news with these two formulas is what you would think and hope happens actually does happen here. So let me try to read my inflection if you can. So when we multiply complex numbers, we multiply r and we add theta. So what do you think is going to happen when we divide complex numbers? Let's see. So what happens, everybody, is you divide the r's, and what do you think we're going to do with thetas, everybody? Subtract them, and that's what happens here. So instead of multiplying r's and adding theta, we divide the r's and we subtract theta. And that's how we get our new angle. Same complex number. This is how we represent every complex number in polar form. R, our new r, new theta with the cosine of theta and I sine of our new theta. So here's how I'll write it. In this case, divide the r's, what are called the moduli, so to speak. So divide r and subtract the thetas. I'll be formal up here, but I'll put a little theta on the back. All right, there you go. So again, exactly what we sort of wanted to have happen, happened. All right, let's check it out. Let's do example 4. Not too bad here. So here's what I have, everyone. Z1, divide by Z2. Divide the r's, so 24 divided by 8, and subtract the thetas. Again, I like degree mode. It works out nicely here. I sine, same deal, everyone. 300 minus the 75. Okay, absolutely perfect. I think we're in a good position here. Let's see what we end up getting. 24 divided by 8 is 3. And I get cosine. Looks like 300 minus 75 be 225. And then I sine, same deal, 225. How does that look? Divide the r's, subtract the thetas. And that's your answer. It's as pretty basic as it gets. That's your answer in polar form. So just working, manipulating numbers in two different forms. At this stage, we should be pretty comfortable with both polar form and rectangular form of a complex number. Okay, good. Now I would encourage us, let's see if we can convert this. So know your unit circle again. You do know the cosine of 225 degrees. Down in that third quadrant, everybody, cosine of 225 is negative root 2 over 2. Here's my I. And then sine of 225 degrees, also, everybody, in the third quadrant. And if it's in the third quadrant, sine is negative, happens to be negative root 2 over 2. How about we distribute, everyone? Take that 3 and multiply it inside the parentheses, if you would. And I think we're ready. So when I multiply the 3 into the negative root 2 over 2, it's not pretty, but it works. And when I multiply in here, just careful with your signs, I see the same thing. 3, and again, just however you want to do it. 3 root 2 over 2 times I, or 3I root 2 over 2, whatever works for you. Doesn't matter to me. Okay. I divided the r's, and I subtracted the thetas, and then cleaned it up. Okay, let's do 4b. So, z1 divide z2. 50 divided by 5 is going to give us our 10. New angle, when I do the operation, 4 pi over 3 minus pi over 3. And then I sine, same deal, everybody. New angle, accomplished by subtracting the two angles together. Divide the r's and subtract those thetas. As I already mentioned, 50 divided by 5 gives us our 10. Anyone come up with an angle already there? It's in radians, but it's not too bad. Have the denominator the same, so 4 pi over 3 minus 1 pi over 3 would be 3 pi over 3. It's pi. There you go. Not too bad. And same deal here. So again, if you're unsure of that piece, let me know, but should get pi right there when I combine those two angles. And there is your polar version of our answer. So that is our product. That's what happens when we multiply those two numbers together in this form, as we have seen and proven. I'm sorry, divide in this case. Now, let's go ahead and convert this on over. Visualize that unit circle. Cosine of pi is definitely -1. Sine of pi is 0. And bring in the arrows, everybody. You're ready to bring them in. The 10 comes in. 10 times -1 is -10. 10 times the 0i, yeah, it's just 0. And there you go. So you just get a real number out of it. So dividing these two numbers gives us -10. If I converted each one of these to rectangular form and did the division like we did first semester pre-calc, you'd get the same answer. Actually, quite a bit harder, I think. This works out, I think, in a little cleaner way. So you could see some operations better rectangular, some polar. Without a doubt, powers and roots better in this new form, the polar form. So as I said, what we'll do here just at the very end is set the foundation, and we will pick it up, obviously, on the next notes worksheet. So I hope you're doing all right so far. All this lesson is manipulating and performing operations on complex numbers in two different forms. Rectangular, which is mostly first semester stuff, but now this polar form and working with that. Okay, guys, let's see what z squared would be. Then I'll tell you what z to the third would be, and then you tell me what our formula beginning tomorrow's lesson will be. So here's what it's going to be, guys. I'm going to take this, and I'm going to square it. Now, I hope everyone is okay with the fact that when I say square it, I mean times itself. So if you would, and here's another great one. As I said, I was hoping you would maybe see when we did our proof at the beginning that wonderful sum formula for cosine and sum formula for sine. In this case, I'm wondering what you see. I will repeat once, and if you recognize it, wow, give yourself a great pat on the back there. Okay, so here's what we're going to do. I got to deal with r's, I've got to deal with those thetas. I'm hoping you're all right with the fact that same deal, order doesn't matter here, so I'm eventually going to have to do r times r. R times r is r squared. No issue whatsoever. Just like my proof before, I'm going to take that and FOIL it with that. And so the best way to do this is exactly the way I kind of did it before. First, outside, inside, last. But I'm going to do the first, then I'm going to do the last, and then you're going to stare at it for a second. You ready? Here we go. Cosine of theta times cosine of theta is cosine squared theta. All right. There's your first. One down. 3 to go. Here we go. Last. I times I is I squared, so that's -1. All that's going to do is change this to a minus. Sine times sine is sine squared. As I said, everybody, stare for a second. What is that? Okay. Now let's go outside and inside here. So here's what I'm going to have. And outside, well, it really doesn't matter, but I'm going to get an I. I'm going to do sine theta cosine theta. Okay. Inside, another I sine theta cosine theta. Now this one you might not be able to see right away. I still need just a touch of work on this. And I will do that in my next step. But as I'm doing that, I'm curious, have you seen it before? Yeah. Do you know what it is? Not sure. Well, let's do one more thing with it first here. Keep staring at it. I'm going to rewrite it one more step. And then over here, everybody, here's what I'm going to do. I'm going to keep my I out. I'm going to factor out the I. And do you see I have two of these? Sine cosine, which means I have two sine thetas, cosine thetas. Now, does that look familiar? Well, let's see. I know the suspense is killing you if you don't know it. But that, everybody, is what is called the double angle formula for cosine. So as a matter of fact, that is actually just the cosine of 2 theta. Double angle, remember that? Formula for cosine. Cosine squared minus sine squared. Then, guys, I put my plus I, and now that I kind of gave away, does that look familiar? That was one of the easier ones. That was the double angle formula for sine. And that, guys, is z squared. Let's put that right there and box that up. That's z squared. Notice what I did. Squared the r, and then I had to take my theta and multiply it by 2. Wow. Double angle formulas coming back to haunt us. Hey guys, I'm going to give you z to the third. Want to know what it is? Here we go. You would have to take r cubed, and it shouldn't come as a great shock. Remember, math is all about patterns. That's what it becomes. Could you probably picture now z to the 4th, z to the 5th, z to the 6th? So raising any complex number to any power? Well, this is where we start tomorrow, everybody. When I raise a complex number to a power, I have to raise r to that power, and I have to change theta by multiplying it by whatever n is. And that's how we'll start out with tomorrow's lesson. So focus primarily on the multiplying and dividing, but it was good for us to set up a little foundation today with this piece. It makes tomorrow's lesson, which is complicated enough as is, to make it a little easier. This is what is called, and we will see it tomorrow, de Moivre's theorem. French mathematician looked at powers and roots. So the two operations, the two killers. We shall get them, and we'll thrive. We'll get it. All right, guys, in the meantime, let me know if you have any questions at all, and try some of the individual problems if you would.